Hi everyone, I'm Ashlesha Patil and I'm joined by Emily Van Milligen to discuss our ongoing efforts on quantum network design, protocols, and algorithms. So, as a part of Thrust 1, we are working on various entanglement routing protocol in a quantum network, but it is also important to study how to best schedule shared entanglement generation between various user groups with a variety of applications. And when we are generating shared entanglement, it is important to mitigate hardware imperfections such as uh, quantum memory decoherence or detection errors to ensure that the final shared entangled state is of the desired quality. And a quantum network should also be able to serve a variable number of users while the network parameters might also be changing. So it is important to be able to model this dynamic nature of the network. We uh, quantify the performance of our network in terms of entanglement rate in ebits per second and the delays involved in establishing the entanglement. But when we consider noises in the network, fidelity can also serve as a performance metric. So I'll discuss a protocol that distributes maximally entangled states in a quantum network at a distance independent rate using only local link state knowledge. We have also developed the capacity region of a single switch, and we plan to extend this work to a quantum network. So the protocol I'll now discuss, like I said before, distributes maximally entangled states in a quantum network, which allows neighboring repeaters to perform bell state measure, neighboring repeaters to fuse three or more qubits to improve the rate versus distance scaling. So here you can see that the links are created between neighboring repeaters independently and identically with probability p. And every repeater that is not Alice or Bob performs this joint multi-qubit projective measurement on the GHZ basis. So this measurement again succeeds with probability q, and the end result is potentially one or more GHZ states shared between Alice and Bob, as shown in this figure here. So we see that the protocol translates to a percolation problem, and we get a region in the PQ space. Uh, the region is defined by the sidebound percolation region. And in this region, the rate stays constant irrespective of the distance between Alice and Bob, but decays exponentially outside the region. And we see that this distance independent rate is impossible to achieve using only Bell state measurements. Emily?
Thank you, Ashlesha. So currently we are also investigating the benefits of including time multiplexing in entanglement routing protocols where repeaters perform BSMs. So first, all the repeater nodes will attempt to generate entangled links with their neighbors with success probability P for some number of time steps. These time steps are called the time multiplexing block length. So afterwards, all the repeaters will then use local link state knowledge to perform Bell state measurements determined by our distance-based routing protocol, which will succeed with probability Q. So an example of this is given by the figure on the left. Ultimately, our goal is to maximize the average rate of entanglement spread between two users, Alice and Bob, by finding the ideal time multiplexing block length for different network conditions. In the absence of decoherence, we have found that time multiplexing can only help. In the case where p equals 1, the rate doesn't improve with time multiplexing, but given p is not equal to 1, we find varying improvements to the rate depending on the relative positions of Alice and Bob. So that's shown in the diagram to the right. We're working with an undergraduate in our group, Joshua Jacobson, to continue to extend this time multiplexing model to the GHZ protocol that we showed you on the previous slide. So next slide. Our next steps are extending this, our work with time multiplexing to other protocols and to evaluate other network topologies such as random networks. We're currently developing a dynamic program that optimizes network performance for given parameters with Dr. Gayane Verdonian, which we plan to use as a benchmarking tool for protocol development. We want to service multiple users with various applications simultaneously. And for any of our protocols to be robust, we need to include noise models and schedule noise mitigation strategies such as purification, distillation, et cetera. The work on the capacity of a single switch will also be extended to that of a network, and algorithms will be designed to achieve that capacity. So thank you all for listening, and thank you to all of our collaborators.